Buddy, it's nice to see you. Nice to see you too. I am doing what can I do
Well, I was hoping you could.
for you?
Well, I was hoping you could. Well, I was hoping you could run a we are in a really good car.
What's the plate
29 T
number?
29 THB03.
2 9 T H
D03. Zero, right.
0.
A class, want your job?
Sure.
What do you call? Three Armstrong.
I don't know. Right.
All right, so well, there must be a reason I played Zootopia clips, right? So you know, we are going to talk about something related to it. But before we start, it's always a good idea. I feel like my pace was too fast, right? So maybe I should say something. Welcome to CSE142. Anyway, all right. So today we are going to continue our discussion on pipeline hazard. But why we are here, because you know, like right now, every processor is a pipeline processor. By pipelining, it means that in your processor, there is a clock control the stages of different parts of your hardware, and different parts of your processor hardware is actually working on a different instruction. So, and ideally, this is what we hope to see in a pipelining situation where every cycle we are outputting something for an instruction, and every cycle we are having result. Well, we are getting a new instruction in, and by continuously supply this pipeline and steadily output stuff from this pipeline, we are hoping to achieve the same CPI as a single cycle design, but a lot shorter cycle time, because right now, each cycle, all you need to do is a stage for an instruction instead of everything for an instruction. However, this is not always possible, because as a lot of you guys learned, we have 3 different types of hazard. Structural hazard, meaning that the hardware doesn't allow 2 instructions to operate concurrently. We have control hazard, which is the time that we cannot determine who will be the next instruction. So it turns out that you cannot have your instructions supply smoothly. And also we have data hazard, which means that your data cannot be supplied in a time when your LU needs it. So it turns out this 3 types of hazard is preventing our pipeline from getting output steadily. And we have been talking about the solutions of structural hazard and control hazard in the past week. So we talk about because structural hazard is just because your hardware design doesn't allow you to do that. So it turns out the best way of dealing with it would be modifying the hardware design. And control hazard, you can also use stall to handle it, but the performance is bad. And you can do static prediction, which you will see in which you already see in your textbook, but we don't talk about it in the class, because I think 2 reasons. One is static prediction is relatively easy to understand, and the other thing is most modern processor has the dynamic prediction. So there's not really a need to talk about static prediction, given we only have 10 weeks. And so the dynamic prediction, we talk about a few different mechanisms. For example, we talk about the local 2-bit, which is a simple one, but relatively effective if you have a loop that is regular. However, if your code becomes more complex, we also see that if you have a global 2-bit 2-label predictor, that will work very well. And for more and more complex cases, we start to see like people, and you have the feeling like, when we try to walk through this GHR example, you already feel like, this is like a machine learning problem. So why not use like perceptron, this kind of machine learning concept, to do it, right? So in fact, a lot of the new processor, they have the perceptron predictor as an L2 predictor or something. So it's also in use, right? So that's what we have. And right now you can assume all your high performance microprocessor has pretty decent branch predictors. So that's the most important message that I want to deliver to you, is that branch prediction is anywhere, and they are doing fairly well these days to address the control hazard. All right, so you can imagine this is our current pipeline. So in addition to the split L1 cache to deal with the issue of structural hazard, we also have the branch predictor, right? So that's where we are. And there is a big type of hazard we haven't talked about, that's data hazard. But before we start, since we watched the Zootopia clips, I want to ask you one question. Within your life, what's the most inefficient place that you ever had for dealing with your business? And if you are the manager or you have the power, what will you do to improve the efficiency? Go. Any idea? This is the question that I feel we have the most discussion, right? And it reflects one thing I told you, like people would memorize their most suffering experience ever, right? So, okay, what's the most inefficient place you ever had in dealing with your business? It's definitely not Disneyland. Where? Where do you have in mind?
So I said the DMV.
Okay, DMV. Okay. Well, how about you guys? Okay. Okay. Driving school? Okay, we can hear that. Well, so DMV, everyone knows. I want to hear the driving school case.
So basically, you would have to register online to get into the school
Mhm.
first. And
You
The
have
way-
to stand up in a line to register for the school.
yeah,
And there is
And
no
to check-
online, there's no phone.
so like back in the days, there was no online. Now there's online, but like
How old were you? How old?
5 years ago
5 years ago? Okay, where is it?
in Saudi Arabia.
Oh, okay.
So like it was online.
Uh-huh.
Now they can do it online. So
Okay,
like,
5
at
years
that
ago.
time, you have to go online,
Mm-hmm.
and like probably you have to wait like for the whole day, and you might not get in.
Wow.
Okay, that just only to register.
And it's
Okay.
in Saudi Arabia, right?
Yeah,
It's
that's-
pretty hot.
Yeah.
Did you do it in summer?
yes.
Oh,
Because they
oh.
have to do it like when they don't have school.
Do they have cover?
It depends.
It depends. Oh,
So,
right.
some
How
areas-
many people ever died because of that? Okay, that's
Yeah,
good to
but-
know.
The first, like, I don't know, the first 50 people online would be in cover. There is one. So,
Okay.
so probably you would go 3-4 times before you register.
Oh, wow.
Yeah.
Because there's only one line, and how many people were servicing that? A lot.
Yeah.
But- A lot of people servicing that.
Yeah, like there's a lot of people, and the system is.
Okay, so there are
bad.
so many people there, but
Yeah.
why it still
The
takes
system
such a
so
long
bad.
time?
And a lot of people will like come in.
Uh-huh.
They don't know the whole thing, so they don't have their paper.
Okay, so they are not prepared and
Yeah.
they don't know anything. Okay, so they have data hazard for sure, right? Because their data is not ready yet, right? Data dependency, data is not ready yet. Awesome, right? Okay, see, totally related, right? What else?
And after you register, you have to go like for 10 days to study there.
Uh-huh.
And
10 days to study there. So the execution time is also very long. Okay,
and each day you have to go to 2 lectures.
2 lectures.
The first one would be like just informations and stuff.
Uh-huh.
And you have to go very early to get in, because if you didn't, then there won't be enough space inside. So they say,
Okay,
Or-
not enough LUs. Okay,
okay. And
memory is small. Okay.
and then there is driving part. So like you go in the
Mm-hmm.
outside and drive with
Mhm.
someone, and you'll have to wait a lot of time there as well.
Okay, again, right? Structural hazard. All right, sounds like a terrible idea, a terrible place. How about your DMV experience? Actually, I feel like the DMV improved a lot these days.
Yeah, so I guess I haven't really been in a few years, and last one I did go recently was a lot better, but it was mostly just takes a really very long time. There's not enough people, I think,
Mhm.
servicing the.
Okay, not enough people. So, okay, so far we all talk about the problems, right? But if you have some idea to improve that, like for example, your driving school, what would you do? Make the registration online. Okay. What would that improve?
So they can serve all the people at the same time.
Well, because they're more the concurrency is better. Okay, what else?
Also, you are like, they would tell you what you have to get before you start that.
Okay, so you have to make sure that, well, when you do online registration, right, you need to have all your documents available, right? So it means that you have to have all your inputs ready to have the registration start and complete, right? Okay, so how about DMV? Why is DMV so slow?
So yeah, partly it's definitely that the people aren't ready with the paperwork,
Mm-hmm,
and so there's you gotta stall out,
mm-hmm.
and there's usually only like a few people. It seems like for hundreds.
Okay, so enormously large amount of requests with relatively small amount of people. Although I do feel like I don't know which DMV are you guys going to, but I do feel like every DMV has more than 30 people helping us concurrently. But surprisingly, it's never enough. I don't know why. Yeah. So sharing my experience with DMV. So yeah, it's okay. So forget about the story because it's totally an illegal story. So I have very bad experience of DMV in California. So when I graduated from UC San Diego, my first job, it was actually in North Carolina. And you know, every time when you move to a state, you are supposed to go to the DMV within 30 days after your move. My place is, and I used to, and I like biking, so I bike to work every day. And every time I bike, I would pass by a DMV. And every day in the morning, I saw a long line. And so I never stepped in because I never decided to stay in because I feel like, you know, I have a lot of work to do. I don't want to waste my day here. Also, there is also another colleague of mine, like he was gone for a whole day. And I asked, oh, where do you, well, I think it was an afternoon. Like he said, he has to leave earlier. And I say, why? Because I have to go to a DMV. Okay, good luck on that. And then the next day, he said, well, he was gone for the whole day. And then the day after I asked, where did you go? And he said, I went to DMV. And I would say, no, you said that you are going to the DMV on Wednesday afternoon, but where you also be gone on Thursday? And he said that, well, when I go to the DMV, I was in a long line. And after it gets to me, they say, oh, it's too late, come tomorrow. So the next day he wake up super early, get into a line and get his stuff done. And the elegant part is North Carolina, they have two types of DMVs. If you want to get your driver's license, there's one DMV. If you want to get your license plate, there's another DMV. So you have to go to separate DMV twice. And after I heard that, I decided that I won't go. And so surprisingly, I don't know why, like you guys know the USPS mail forwarding service, right? So my California license plate registration forwarded to my address in North Carolina. And I tried to submit my payment online, works. And it works for the rest of the 3 years that I was in North Carolina. So I'm the one who keep having the like up-to-date license plate sticker in the past 3 years in North Carolina, even I was in California, also with the driver's license, because I also tried to renew my driver's license online and it passed. Probably that's one of the reasons why they decided to do real ID afterwards, because I can actually get my driver's license renewed when I was off the state. But you know, that was my story with the DMV. Okay, so too long, right? But you know, sounds like everybody has a lot of experience with stuff like DMV. So today we are going to continue our discussion, but also try to tell you how our processors tried to solve this inefficiency problems in executing code. So, but to wrap up our discussion in branch prediction. So you guys must remember these pieces of code, right? Like we have seen this code so many times, right? You have an option, you have a sort, and you have code like this, right? So some of you might think, okay, what does pieces of a code even means? So here's what I'm going to say, right? So this pieces of a code actually stands for this SQL code, right? So if you want to do, like I want to do select count from table where value smaller and a threshold, right? That's pretty much like this state, pretty much like this pieces of a code. Agree? So what this pieces of code is implying to you is that, okay, if today your database table is sorted, it's pretty much like doing this, right? You sorted your database table before execute a set of queries. then you will get performance like having the data sorted here, right? But if you have your data that's completely coming without being sorted, then your performance would be the case where the option is set to 0. So that's the implication of this. So now you know, like, okay, this demo has its own meaning. But right now, what I want you to do a little bit of analysis. So given that's the case, why the performance is better when the option is not 0? Yeah, sorting is always a good idea. Well, you have to decide which column, which attribute do you want to sort. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. What do you guys think? I love this graph. Let's just go discuss for another 90 seconds and let me know what do you guys think. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. Here we go. So after discussion, more of you think it's C now. Okay, if it's C, you guys must agree there are 2 of them correct. So what are the 2 you guys have in mind? What are the 2? What are the 2? What are the 2? What are the 2? 3 and the 4. The number of branch predictions is smaller and the amount of data access is smaller. Okay, you think this is the 2? What else? Any other thoughts? 1 and 3. Okay, okay, so we have 2 versions now. Okay, 3, at least people agree with that for the case 3, right? The amount of branch prediction is smaller. How come? How can you see that? Because we are talking about branch prediction? How can you see that? Okay, so this is the main branch that we have trouble with, right? So saying if your data is unsorted, what do you imagine the outcome of this branch to be? If your data is completely unsorted, you cannot predict, right? Because if your data is unsorted, sometimes it could be larger, sometimes it could be smaller, right? And sometimes if it's larger, small, right? Small, larger, right? So there's no way you can predict it if your data is unsorted, right? But today, if you have your data, so the best case, right? The best case that you can do with unsorted data is that, okay, saying that, so now let's discuss the case where saying that, okay, so now if you have data unsorted, right? The best way you can guess is probably just statably guess one direction, and half of the chances you are going to get it right. Agree? Right? If we pick a relatively median number in a threshold as a threshold, right? That's the best you can reach, right? 50-50. However, if you sorted your data, right, before you reach the threshold, right, every data is pretty much smaller than your threshold, right? So you will miss a few in the very beginning, and then everyone you are going to predict that correctly, right? So except for the very first few, you are going to get 100% prediction. Even though you have a two-bit predictor, it works in this way. However, after the threshold, again, you are going to see that you have misprediction several. And then you can calibrate your branch predictor again to make it almost like 100, right? So with this, you can see, well, the amount of misprediction is a lot smaller after you have your branch, after you sorted your data, right? So we can also see that in the demo. The same demo has been shown in the lab lecture last time. So if you were in a lab lecture, that's actually exactly the same. Exactly the same demo that I'm going to have that I had in the last lecture. But if you were not in a lab lecture, you're going to see it again. So here's the code we had, right? So let me see. Okay, so yeah, again, here we are running this pieces of code, and we are very familiar with the code. So what I'm going to say is that here I insert performance counter, right? So here I start to count all the performance counters, and then I printed this out. And in the very beginning, you can see that we have array data generated with random numbers, and here we also have the threshold number picked randomly. So now let's rerun and then remake this pieces of code, and then I can show you here is the result. Oh, oops. Okay. Okay, so here is what we had. So you can see, right? Again, this is the same sort that you will be really familiar with. So without the data being sorted, you can see the execution time is 0.3 seconds. And with the data being sorted, the same parameter, the same amount of data would have execution time only 0.6. And if you count the instruction count, that's pretty similar, right? And the number of cycles is a lot fewer because the branch prediction actually got improved a lot. And the CPI also dropped from 1 to 0.22, right? So with your data being sorted, there are lots of benefits that you can see, right? And with that, if you subtract the difference of branch misses and the difference of cycles, right? Because these are pretty much, because I'm only counting the number of instructions within that loop, right? So you can see that the instruction count is not changing a lot. All the differences are coming from the fact that you have branch misprediction or not, right? So the difference of branch mispredictions and difference of cycle time, the number of cycles would give you roughly the idea about how expensive a branch is. So from this simple counting, you can see, right, it's 34 here. So it means that, okay, if your branch is mispredicted, it takes 34 cycles to handle it. So it's really a huge penalty that you cannot ignore it. And remember that if L1 is hit, it's only 4 cycles. If L2 is hit, that's probably like 20 to whatever cycles. So branch misprediction is actually more expensive than you can ever imagine, right? From the demo, it tells you that it's actually 34 cycles, very expensive in modern processors, right? So it also tells you, right, that the pipeline diagram in our textbook is very far away from reality because you only see 5 stages, 5 cycles, right? So how come there's 34 cycles? So this data also tells you that modern processors, you might have more than 34 stages in your pipeline. And that's indeed the reality. So, so that's why we have to deal with the branch prediction, right? But from this demo, from all what we have learned so far, it delivers an important message is that nowadays your modern processor has very good branch prediction. However, if you don't sort your data, or if you cannot find a way to make your execution pattern easier to predict, then you are going to suffer this 34 cycle delay every time when you meet a branch. All right. So later this week, we will talk about some programming techniques to make the behavior of your code easier to predict. But for now, let's continue our discussion on the third type of pipeline hazard, that is data hazard. So again, data hazard means the time that we have an instruction who is waiting for an input before it can really be executed. So like your driving school example, like a lot of people's DMV example, right? You might wonder like, okay, why do people in front of me take so much time? Because the data is not ready, right? Like, where's your ID? Oh, let me find it. Okay, it's in my purse, it's in my bag. Oh, I don't know where is it. Let me call my friends. Okay. Oh, it's at home. Okay, sorry. Right. So this kind of stuff, right? So whenever you meet this kind of issue, like, okay, your instruction or your job cannot be done because of data is not ready, that's called data hazard, right? So that's data hazard. So the reason why, or say the source of data hazard, is because you have data dependency, right? Saying that if you are dealing with a business that doesn't rely on any additional data, you just go by yourself and things will be down, right? Then there's no data dependency at all. However, if today you are dealing with a business that relies on some other data than just the instruction itself, then there must be a potential of data dependency. So for example, and data dependency is everywhere, right? So for example, today, if you want to go buy lunch, then if you don't have money, right, then there's no way you can get lunch, right? So I know there are many other exceptions, but let's talk about normal cases, right? Like, but most of the time, right, you have to bring something else. And think about in your x86 instructions, right? There aren't that many instructions that can proceed without data. So that's why we have to care about the problem of data dependency and data hazard seriously. But we know that data dependency is the source of data hazard. So I wanted to revisit these pieces of code, which we have been pretty familiar with in last week again, and tell me how many data dependencies do you guys see in these pieces of code? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Okay, looks like we need some discussion. So why don't you guys go ahead and discuss with each other and tell me how many data dependencies do you guys see here? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, see, that's the power of peer instructions. The more of you think it's D, but still quite a sufficient amount of you think it's D. So B and D. Okay, we need a debate. What do you guys think? Where are we seeing the data dependencies? Okay. Okay, so you said where?
So the first instruction and the fourth instruction.
Okay, so there's one pair here on EAX, right?
Second.
And the second and third. Okay. Any objection on this too? What else? What are the other two you guys have in mind? Sounds like there's only two. What are the other two that you guys have in mind? We have 45% of you think it's D, right? What are the two? The other two? Okay, so indeed, for this pieces of code, we only have two. And I guess some of you might be thinking about this RDI, RSI, right? But remember, this RDI, RSI, when you see this, right, it's actually a pointer to a memory address. So when we talk about data dependency, most of the time we are just talking about the registers. So as long as you don't modify the register value itself, it's not considered as a data dependency. So for example, if someone is indeed modifying RDI's content, then there may be a data dependency because of that. However, here, we are using the RDI to calculate the effective address. We are using the RSI to calculate the effective address. Here, we are using the RDI to calculate the effective address. Here, we are only using the RSI to calculate the effective address. So indeed, there's nothing in this pieces of a code is modifying the memory locations. Modifying the memory addresses that are stored in either RDI or RSI. So that's why there are only two considered as data dependencies here. All right, so let's give you guys one more chances. So for another type of swapping, How many pairs of data dependency are we seeing here? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, let's take a look. Okay, we got many of you have different answers. So why don't you guys talk to your friends for another 90 seconds? You know, maybe the two that you are thinking, or maybe the three that you guys are thinking will be different from others. Go, discuss. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let's see. After discussion, slightly changed, right? We see the shape is moving toward E. So looks like after discussion, when you unionize your question answers, you will feel like, okay, there are my three is different from other people's three, right? So we put everything together. Okay, so what do you guys have? Which one and which? Any idea? First EAX to the second EAX, right? So in moving instruction, the output is EAX, right? But for exclusive or L, right? And S86 has really complex format in a way that if it's an arithmetic instruction, the target is also serving as one of the source. So this is also a source. That's really annoying. But because of that, right? So there is a data dependency here because the output of the first instruction is indeed the input of the second instruction. Who else? The second EAX? Okay, right. Again, for this EAX, it's the output, but it also served as the input of the third instruction, right? Okay, who else? Okay, the third and the fourth, where do you think you are seeing the connection? Uh-huh. Okay. Okay. Awesome, right? So here's the thing. For move instruction, right? So move, we are just moving the value of EAX to the memory address pointed by RDI. So in fact, this EAX is only serving as the source. However, you got it right, right? So for the second instruction, if you look at the EAX, it's again used by the same value generated by the second instruction is again used by the fourth instruction. So that's actually the third one. What are the others? Okay. Fourth instruction and right. Also this one, right? Okay, so 1, 2, 3, 4, 5, right? So you see there are 5 of them, right? So 5 of them having this data dependencies. See, that's why, and we say, whenever we say there is a data dependency, there is a potential of data hazard, right? So even though this pieces of the code and the previous example, they have the same function, but because the way how you write it now, you have more data dependencies in your code, which meaning that there's a higher likelihood that you are going to meet the problem of data hazard. So let's see how many of them really turn into data hazard. So saying that today I have an x86 processor that has 100% cache hit rate. So you can assume that your L1 data cache, whenever you want to access, is 4 cycles delay. So if that's the case, how many pairs of data dependencies in the following x86 instruction will actually become data hazards? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I like this graph. So we need some discussion for sure. Why don't you go ahead and discuss with your friend and see how many of the data dependencies really becomes hazards? All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let's see. So now more of you think it's C. That's the power of group discussion, right? So what are the two, how do you solve this problem? We only have 2 data dependencies in this pieces of code, right? But how do you know that all of them become data hazard? Okay. Uh-huh. Okay, including fetching, decoding. Okay, so it's pretty much like the first cycle, we fetch this instruction, right? And then the second cycle, we decode the first instruction and fetch the second instruction. So far we have no trouble with it, right? And then we say for memory operation, it takes 4 cycles, right? So then the first instruction will be going into its first memory operation, and the second instruction will be decoded, and the third instruction will be at its fetching stage, right? So now, so far so good, right? How about the next cycle? Are we allowed to do this? Are we allowed to do this?
But if your hardware is good.
Yeah, right. So if it is pipeline, right? If it's pipeline, then you can assuming that, okay, the memory pipeline can accommodate different stages of access. Okay, fine. So let's have it go through, right? Assume this is a pretty good pipeline processor without structural hazard. Okay, that's good. Okay, so no problem at all, right? How about the next cycle? I have a problem because the third instruction depends on the second, right? So now, right, we thought we want to do this. However, here we want the EDX. However, the EDX can only be ready after this instruction finish execution, right? So this is not possible, right? And if you keep going, right, you will figure out that, okay, this one is also not possible because here I want the value of EAX. However, it's still in the memory pipeline yet, right? So 2 of the data hazard will become a data dependency will indeed become data hazard. So this is one way of drawing it, right? And I also think this is another more space-saving representation. So if you want, and actually in the rest of the talk, the lecture, I will do this a lot, is that because this is easier to do if you have an Excel, right? So that's why I want to teach you this. So for this kind of spreadsheet style diagram, right? This is actually cycles, right? And this is the pipeline stages you have. So you can imagine at the first cycle, what's occupying your instruction fetch stage is your first instruction. And then your first instruction advanced to instruction decode, and the second instruction coming into the instruction fetch, right? And you want to do this. However, right here, at this point, right, we don't have the EAX available because for the third instruction, we actually want the second instruction to be finished. However, the second instruction can only be finished at this point. So this is not possible, right? And same thing, right? For this instruction, we want the EAX to be ready. However, your first instruction can only be ready at this point, right? So both are not possible, right? Okay, so again, we said stall is the universal solution of it, right? So you can definitely stall whenever your data is not ready. So when we first time meeting the trouble of data hazard here, right? What we end up doing is that, okay, for the third instruction, right, we just stall. By stall, it means that we just stay at the same state, right? And because of this instruction is blocking at the instruction decode state, the next instruction cannot advance, right? So here, that's why this one also stay at the instruction fetch. And we keep stalling until the first instruction finishes its write back, because that's the only time that we are able to get the value of EAX from the register, right? So you still have to do the first cycle write. And then at this point, sorry. Okay, so, oh, no, okay. So for this one, you are waiting on this one, right? So you still have to get your first cycle. You still have to wait for this one to write back. Oh, okay, so actually it's even worse. So here, you can only retrieve it because it's the first cycle write, second cycle read, right? So this one has to wait here. So there's one more cycle delay, right? So actually, my pipeline diagram is also wrong. We have to have 4 additional cycles in the delay, right? Okay, so you might ask, right? So if same thing here, I think, let me see. Okay, why is it so slow? Okay, I think this one I actually got it right. Okay, so this is the other pipeline diagram that I draw using the expression method, right? So here, so this one is correct. The previous one is wrong. So here, right, because the third one is depending on the second one. So here I'm depending on the output from 2 to continue, right? So you can see we have a huge gap here. 1, 2, 3, 4, right? That's where you see this 4 additional cycles of delay, right? So if you use stall, 4 cycles, right? So now what we are going to talk about is that, okay, is there a better way than stall? So the second one is a hardware solution called data forwarding. So so the key thing here, right? If you check the previous figure, right? Okay, sorry, I have so many animations that I have to show here. How come? Sometimes I hate myself of having so many animations. Come on. I feel like I have to go to occupational therapy one day. Okay, here we go. Okay, so your question would be this, right? So at this point, right, after you finish your M4, actually you already have your EDX value ready, right? Why do we have to wait for the write back? Is there a way that I can deliver the result early? So that's actually the idea of data forwarding. So data forwarding is we add hardware logic or wires to forward your outputs from functional units to another functional units instead of getting everything from the register. So this is the original pipeline processor we have. But right now what I'm saying is that, okay, imagine we have data forwarding from the memory operations to your LU. So you will see this line added, right? This line added, right? This line added. See the animation, this line added, right? So you can pretty much having some mocks selecting, okay, so at this time, I want the input from the memory operations output. Or you can also forward your LU result to other units as well, including itself, right? Or you can also add circuit to forward your complex arithmetic or logic result to other units as well. All you need is the mux to select at this time, where am I getting my inputs from? That's data forwarding. So let's assume if you can forward the data whenever you need, then for this pieces of a code, how many data dependencies would still be problematic in a way that it will lead to data hazard? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's take a look. Okay, definitely some discussion, right? So go ahead and discuss with your friend and let's see what's going on. A timing cost. Typically we assume 0. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. All right, let's see what you guys get. Okay, looks like we still have a pretty complex situation. So again, right, if you want to solve this problem, essentially the easy thing to do is to draw a pipeline diagram. No matter you want the traditional way or the spreadsheet way, right? So let's show the traditional way a little bit again. So if you have data forwarding, right? So what you could do is, you know what? I think I did something wrong here. So, okay, let's forget about this. So let's look at this one. Maybe I get it right this time. So, so we have two data dependencies, right? The first and the fourth. So if you have data forwarding, pretty much means that when the second instruction entering its when second instruction is done with its M4 stage, the next cycle, the third instruction can start with its M1 stage, right? So let's see. So what you would do is that, okay, now the second instruction finishes its M4 stage, and now finally we can move we can have this data forwarding here, right? From the output of M4 to the input of M1, right? That's when we can start 3, right? So with this data forwarding, there's only one, and you only have to stall for 3 cycles because of that, right? And in fact, if you look at 1 to 4, right? If you look at 1 to 4, it's not necessary to have any data forwarding in this case, right? Because they are already far away from each other, right? So for this case, there's only one data forwarding required, and there's only one data hazard we are meeting because the data dependence between 2 and 3. But for 1 and 4, although they have data dependency, but there is no stalls incurred because of this data dependency, right? So with data forwarding, in fact, for this instruction sequence, we don't see a demand of stall again when to deal with the data dependency between 1 and 4. So there's only one data hazard here because of the dependency between 2 and 3. All right, and at the same time, we see the number of delays is reduced from 4 to 3 because of data forwarding. Right? Question?
Yeah, but are you not also like storing?
Yeah, but you have to stall the 4th instruction in the fetch stage is simply because the instruction decode stage is occupied by the instruction 3.
So that wouldn't count as
We don't count this as a data hazard because of 1 and 4. Okay? Question?
So the reason you don't count 1 and 4 as data hazards anymore is because now the data forwarding is needed someone to set the delays.
Yeah.
Gets rid of that hazard.
And also you have the data forwarding. Okay. Good. Okay. So this is what we get with data forwarding here. So now I'm going to skip this real quick. So, okay. So I originally have another question, but I think it's good enough for us to skip that question. So you might wonder, right, okay, even though I want to talk about that question, I don't think I have the answer. Okay, anyway, okay, so now let's talk about another code example, right? So this is another code example, and this is a, oh boy, why my order is wrong. Okay. All right, so this is the swap, another version of the swap that I have, right? So if you look at the swap, and if you draw the same pipeline diagram, even with data forwarding, with a very optimal situation that for XORL, I only assume the delay will be 4 cycles. Even with that, with data forwarding, right? And you will see like there's one stall because of the data dependency between 1 and 2, and another stall because of the data dependency between 2 and 3. And then you will see another stall because of the data dependency between 4 and others, right? So like here, you see another stall, right? So if you use the exclusive OR way to write your swap, you are going to see like not only the increase of instruction count, but also the more data hazard that you are going to have in your code, right? So that's why I keep saying that that's not a good way of writing swap because of data dependencies, because of data hazards, right? Okay, and here I think you really see how different it is, right? The amount of cycles you need is a lot more. All right. Yeah, like previous code, I think we only have 14 lines, but for this one, we have 21 lines, right? So it's like 1.5 times more. And I hate myself for having so many lines. All right. So we're done with the swapping example, but let's try to see. Sometimes you will think, okay, more of the time I'm looking the code example like a loop. And let's see, right? So this is the implementation of this particular loop. Is the code of getting the data within an array, right? And have the summation of it, right? So if you execute this pieces of a code, you can definitely draw a pipeline diagram like this. And based on the code that we have, you'll figure out that, well, we have a data dependency between ECX here, right? And this data dependency, because you have to execute this add L right after the move L. So you definitely have to wait for the one finish its M4 stage, and then you can start forwarding data and start executing too, right? So this is pretty much the execution diagram. So now I have a question for you, right? So if this is the loop and this is the basic block, right? So you guys, if you were in the lab lecture, you know the basic block means that the first non-branch instruction until the first branch instruction you need after this non-branch instruction, right? So for this 6 instructions, so for the first 5 instructions, they definitely a basic block. So if you are allowed to so if you are the compiler, right? What pair of instruction would you reorder without affecting the correctness of the code? All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so most of you think it's B, right? So okay, so maybe we can just fast forward this question. So as you guys see, right? So the answer is indeed B, and the answer is right. If you look at the code we have here, right? We have, if you reorder B and the 2 and 3, right? It doesn't really affect the correctness, right? Because for 2 and 3, right? Do they have data dependency? No, they don't have data dependency, right? But if you push 3 a little bit further, you can actually reduce the amount of cycles that you need to wait before one generates the result, right? So originally you have to wait longer here, but now you only have to wait for 2 cycles, right? So that's what a compiler can do, right? But as you can see, it's still pretty limited, right? And in fact, compiler could be more limited if we talk about another cases. Okay, so but at least you know, okay, with compiler optimization, you can also improve the performance in some sense. Okay, so Why do I have this 2 here? Okay. Okay, so far, a quick question.
Oh, sorry. I guess kind of related somewhat. So if we didn't have line 4, what would jump not equal do? Like it would just look what is the previous value in like the register?
Well, it will read for the current flags. So whatever the previous comparison instruction is, it will continue to read that value. Okay. So far you have the question, right? So far we only see one pipeline. And a lot of you might have the question like, in my demo, I actually show you the CPI could be less than 1, right? How does that happen, right? Because so far, if you have a single pipeline and it seems like every cycle I fetch 1 instruction and output 1 instruction, then my maximum CPI should be 1. But how come, Professor, in your demo, right, we get like CPI less than 1? Here's the thing, right? Look at the pipeline we are having right now. We are actually having a lot of functional units, right? So if you have a way to utilize all of them at the same time, you are actually able to have multiple instructions in execution. And with that being enabled, we should be able to receive a CPI that is less than 1. Agree? However, what are we missing now? Why can't we activate them all together at the same time? Or why are we restricted by CPI equal to 1 at this time? What? I have 1 processor? What? 1 pipeline. I can still, well, how can I enrich this pipeline to fully activate all the LUs? Why my CPI is currently 1? Because I can only fetch 1 instruction, decode 1 instruction at the same time, right? So if all you can do is every cycle, I can have 1 instruction in a pipeline, into the pipeline. What's your maximum CPI? 1, right? So what you actually have to do is that you want to fetch and decode more than 1 every cycle, right? So it would enable the potential for you to have 2 instruction or even more instruction in execution at the same time. So here is the idea called superscalar, 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 superscalar. Superscalar is the case, right? If you compare the diagram, right? What's the difference, right? Oops. The difference is simply you have a wider instruction decode and instruction fetch unit, right? So the idea of superscalar is that, okay, since we have many functional units now, right? I fetch, decode, and issue more than 1 instruction each cycle. So theoretically, my fetch width, which means that how many instructions can processor fetch, decode each cycle, and my issue width, how many instructions can I put into execution, would plus the number of functional units that I have would determine my CPI now, right? So my theoretically minimum CPI would be the minimum of issue width, fetch width, and decode width determined by this 3, right? So saying that if I have a processor with fetch, decode, and issue width equal to 2, which means that I have the capability of executing 2 instructions at the same time, fetch 2 instructions at the same time. Let's see what's going on here. So at the very first cycle, right, I would be able to now fetch 2 instructions at the same time. So that's why you see 1 and 2 are in the pipeline now. And in a second cycle, right, I can continuously fetch 3 and 4 and decode 1 and 2, right? So I have 2 more instructions in the pipeline. And now in the next cycle, okay, here we have a branch instruction, right? And if I don't have a predictor, I can only fetch 5. Do you guys agree with that? Okay, so now I have to decode 3 and 4, and 1 and 2, I can put them into execution. And continuously in the next cycle, well, because I can only, because I have the issue of I would say control hazard. So I would not fetch more instruction. And in the meantime, if you look at instruction 3 and 4, 3 is depending on the first instruction, right? So actually 3, the 3 has to stall in the instruction decode cycle. And as a result, you cannot actually move the 5th instruction into instruction decode stage, right? So there is indeed a stall here, and you have to keep the stall until your the first instruction finished is M4 stage to continue, right? So that's how you see these pieces of code would play in this pipeline. Okay, so here you might think, okay, theoretically, right? I thought these pieces of a code should give me a theoretical CPI equal to 5. But if you check the amount of time you spend, right? So for this 5 instructions, you actually spend 11 cycles, right? So your CPI is far from 0.5. In fact, your CPI is very close to 2 in this case. So you might think, how come the superscalar is not helping at all, right? So we are going to give you some idea how can we make the superscalar pipeline great again. However, before you leave the classroom, a few things that I want to talk about. So when you submit a grade scope regrading request, I am the one who reviews it, and I feel a lot of things that I want to talk about. So sometimes I do see requests like, okay, have detailed explanation about the answer of this question, but I'm not a mind reader, right? I'm not a fortune teller. So I have no way to judge if you really know your context in this detail given the answer you have, right? I cannot elaborate more from your answer. So again, for that kind of regrading request, it won't be accepted, even though you put like an article explaining why your 1-sentence answer should be given grades. So we won't do that. So here is my advice to you. So it's not about this course. And in fact, for technical interviews, as an interviewer, right, we want to see our interviewee can be precisely answer the question. Don't waste our time. And in fact, a lot of people, that when they do their interview or when they answer their questions, they try to pull a lot of knowledge from their brain because that's all they know. But whenever you do that, it just reveals that you don't actually understand what the interviewer was asking, right? So it's actually reveal your weakness. So don't do that. Not only for your final exam, not only for your assignment, not only for your lab, but also for your interviews. And important things goes faster. So another thing is that everyone has limited concentration, right? Like I know maybe the first 10 minutes in this lecture, you are super concentrated, but now you just want to go, right? Same thing as an interviewer, right? I would only be concentrated probably the first seconds when I ask you a question. So if within the first seconds, I don't hear the keywords that I like to hear, I would give up on you. So same thing, if you are answering your question, try to put the most important keywords in the very beginning so that I know, okay, this guy really knows something, then it will attract me to stay in your answer and read carefully, right? But what you try to do is like throw a lot of keywords that is irrelevant in the very beginning. Okay, sorry, I'm not going to read it. And again, we cannot read your mind, right? So a lot of people have trouble with getting ace their interviews because, well, they just give very simple answers and without explaining what's going on, right? So it's not going to help, right? And also, finally, show your work, right? You would never thought that I can answer a leak code question, but impress the interviewer with saying that, okay, this question must be solved by DP, done. No, you have to show how you use DP to solve this problem, right? So if you know I have to do this in interview, why don't you do this in your midterm and final or your assignments? Agree? So, and in fact, answering exam question or assignment is the best chance for you to practice those skills. So if you don't practice the skills every day, right? And spend additional time to like, practice leak code problems, questions. I mean, it's not going, I think something is wrong here in the process. Okay, so that's my advice to you guys, and hopefully you will get it. And the most important thing is the last reading quiz we'll do this Wednesday before the lecture. This is summer session so fast. Last reading quiz, right? I'm going to miss you a lot after the summer session for sure. But for now, at least don't forget to complete your last reading quizzes. Other than that, I will see you tomorrow.